So do any of the four of you have any questions? Oops. Oops. What's going on here? Okay. Well, let's just get going then. So today we're gonna finish section 1.6, and then we're gonna review for the entire unit 1. We may need to talk some more about the project, and that will be that. You know what? I'm going to do this as a PDF. Okay. So one 6 is a very short section because there's really there's just one thing I want us to work on in 1.6, and that is scientific notation. And so here we're converting numbers between decimal and scientific notation. And then I want to add to that. He doesn't have it here. Come on now. We'll do option 3, calculations with scientific notation. And specifically, I'm going to show you how to do it in Desmos. You can do it in any calculator following the same thing that we're doing here. But first, how'd you all do with the 1.5 worksheet? Anyone have any questions on the 1.5 worksheet? Oh, we did it in class, didn't we? Not that that means you shouldn't have questions, but this should have said change. This should have said change. Okay, well, awesome. Then we don't need to talk about it unless y'all want to talk about it. Okay.
Can I ask a question?
Please.
I'm sorry. I did okay with the worksheet, like looking back at it, but then like re-looking at it and looking at other examples, I'm still a little shaky on finding the actual versus the relative. I guess just the wording on when that happens.
That's a great question. Yes, 100% that makes sense. So, and part of it is I don't think I've been super consistent in the worksheets and other places about using the exact same word. So there's actual change that we sometimes just call change. And that is new minus old. That's the difference between the two numbers. So how far apart are they? And that's just the amount of change that's occurred. Whereas relative change or relative difference is the same thing as percent change, which is the same thing as new minus old divided by old. And this is always a percentage. Well, the decimal version of a percent. It's so weird that it changed writing. So what we do with this is we then multiply it times 100, and that becomes a percent. And so the reason we do this is is to really understand like the significance of the change, right? Like we can talk about $1 billion difference, $1 billion increase or decrease in spending, but if it's relative to an amount from $1 trillion, then it's essentially zero in terms of a percent change. So it's one of the ways we can make sense of really what politicians do to us all the time when they talk about how money is spent. So politicians will try to prove a point, maybe, or make, I hate to talk bad at politicians, but maybe I don't. You can pick which one of these you want to talk about, and they're mathematically correct. It's just one might suggest something, whichever number you talk about has a different suggestion about priorities and the rest. Like, for example, one of the common ones I've heard is getting rid of funding for the arts. And people will say, we spent $100 million on paying for like people to draw pictures of such and thus. Well, that $100 million relative to the budget of the federal government is $0. Right? Like it's 0% of the money we send out. So getting rid of the $100 million for funding of the arts has no effect on how money is spent. But it could be, say, I think it's called whistleblowing or whatever. It's a rallying cry for a group of people that think spending money on the arts is a waste of money. We can do the same thing on any other kind of topic where the amount of money spent to an individual like myself sounds like a really big number, but relative to all of the spending, it's essentially zero. Like the border wall. Remember back when President Trump was talking about funding the border wall, it was like, what was he wanting? Like $3 billion or something? Relative to the budget, that was like 1% to 2% of the money we allocate. So it was nothing. And of course, the left got really angry about spending all this money on their border wall, whether it's justified or not, whatever, that depends on your point of view. In terms of relative to all of the money spent, it was a fraction, it was a tiny amount of money, which is hard to understand for me that only has, $500 in my checking account right now, and I can't wait for my paycheck to jump in so I can pay my bills, kind of thing, right? So that's conceptually what you should have in your head when you're thinking about these two things. One of them is just the amount, how much change. And the other is, well, compared to a previous amount or compared to a total, how much difference is there as a percent? I don't, Maya, does that help at all, or is that just getting crazy?
No, that helps. Thank you.
Okay, good. Other questions you'll have about anything? So I changed the word here from change to difference, but question A, like we did in class, was just new minus old, saying how much money difference did we spend? And then question B is new minus old divided by old. So what percent change happened? Usually the relative change is the more accurate description of what's going on than the amount change, if you're trying to make a point. And then just as a reminder, I know we did this one, but there might be people watching the videos that need that reminder and missed the first one. Whenever you're interpreting the relative, this again should say change, you're talking about when, what, and how much. Those are the three key things you got to talk about. Okay, well, let's talk scientific notation then. Our author has an interesting talk here. He says in 2018, the average household in the United States had a little over 103,000 in debt. Yikes. So debt is money you have to pay back. So this is probably credit cards, maybe your mortgage, maybe your car, the debt on your car, maybe it's your student loans, etc. Yes, that's not good. It's terrible. The federal government's total debt is this number. Could we read that? Let's see. We have hundreds, 100,000s, 100 millions, 100 billions, trillion. So our author didn't tell us when he wrote this textbook, but it's between 2018 and 2022. I think it might have been 2020 when he revised it. So that's $22 trillion, $617 billion, $777 million, $240 trillion. That number, I screwed it up. That's a ton of money. It's actually terrifying if you think about it. Yeah, he's like, I bet 3/4 of the population can't even pronounce that number, let alone comprehend how ridiculously large it is. Yeah, here's how to say it, which I didn't say right. So then he's like, well, what if you decided to pitch in and help out, send the government $10 to pay it off? And he's like, well, that's this percentage of the debt. That's less than 0%. That's not true, but it's a super tiny percentage. And the point here is this is a really, really big number, and this is a really, really small number, and writing those is tedious. And if you're in the science world and you're working with, say, the distance the space shuttle has to travel to get to the moon, or the orbits of the planets around the sun, or all these other different things, or measurements in a microscope that are really tiny, you need a handy way to work with the numbers, and that's where scientific notation comes from. And scientific notation is based on powers of 10. So I'm going to write out some powers of 10 stuff, because I think it can be helpful. First off, the author also puts in there some exponent notation. So if you don't know what an exponent is, it's a little number raised to a number. For example, 2 squared, that's repeated multiplication is what that means. It's 2 times 2, which is 4. So then 2 cubed is 2 times 2 times 2. We multiply 2 times itself 3 times, and we get 8. So that's an exponent. And we use exponents in scientific notation. They just happen to be powers of 10. So it looks like this, and we call this the tens place. Then we get 10 squared, which is 100. These are the ones we're probably all super familiar with. Hundreds. And then we get 10 cubed, and this is where we start getting more interesting. That's 1,000. So we'll say thousands. And then we often skip to 10 to the 6th power. So that means we're multiplying 10 times itself 6 times, and it's going to have 6 zeros after it. And this happens to be millions. And then the next common one is 10 to the 9th. So 1, 2, 3, 1, 2, that's 3 sets of 3, which is billions. It used to be that someone who had $1 million in their bank account was the top 1%. You know, I'm sure you've heard the term a millionaire. And there were very few millionaires in the world. I don't know when that time frame was, maybe the 80s, maybe the 70s. You were ultra wealthy if you had $1 million. Nowadays, millionaires are a dime a dozen. Everyone's a millionaire. I mean, not me. Hopefully some of you are. I'm guessing not, but that would be awesome if you were. So getting $1 million isn't that difficult nowadays. Nowadays, it's the billionaires, and there aren't a ton of billionaires in the world. Elon Musk, Bill Gates, there's that guy in India that is now the wealthiest in the world, I think. And then there is no one in the world that is a trillionaire. That's like an impossible number to reach in terms of a single person having that much money. Now, there might be the ultra rich, these billionaires that are trying to hit that mark. They're never going to get it, I don't think. And then we can keep going. I'll do another one. Notice we keep adding 3 zeros to this, and that's these crazy numbers. I don't know that we're ever going to reach a quadrillionaire or quadrillions. I don't think the US could go that far in debt. So this is quadrillion. And then we could keep going, but in terms of money, this, the trillion is the tap out part. Another thing you could think of is that 1,000 billions is equal to a trillion. And then another one, 1,000 millions is equal to 1 billion. And then another one, 1,000 thousands is a million. So that's just language with big numbers. And then this left side, this 10 to the exponent power, is how we write scientific notation. Maybe I should pause there. Does anyone have any questions, or do you need a second to write that? I don't even know if you need to write it, but this is just how to talk about numbers. And you're going to encounter this, you encounter this in the world all the time. This is US debt. Oops, I didn't want to go there. All right, let's go back to our notes then. So I've talked through what this is. And then scientific notation, let me give you a definition of it. He buries it in here. So each extra power of 10 puts another 0 on the decimal equivalent. That's what these are, the decimal equivalents. 10 to the 5th, we can count 1, 2, 3, 4, 5 zeros. That's what's happening. So 5 billion here has 9 zeros. We'd write it as 5 times 10 to the 9th. That's scientific notation. And there's a little rule we use for scientific notation that you need to know. It's going to crop up in the homework and on ALEKS and on exams. And that scientific notation is written like this. We start with some sort of number. We'll call it A. A is a number between, a number between 1 and 10. It can equal 1, but it can't equal 10. The mathy way we write that is with an inequality symbol. We write it like this. A can equal 1 or bigger than 1, and it can get super close to 10, but it can't be 10. Then we often use the little X symbol that tends to disappear for multiplication. In this case, it means multiplication. And we use 10 as a base, and then we use n, and this n is some sort of integer. And if you don't remember integers from your prior math experiences in life, this is what an integer is. Oops. The nice numbers, the nice counting numbers, including the negatives. So that's what scientific notation looks like, the general form. Let me try to write scientific spelled correctly. That's a fail already. All right. Apparently, I don't know how to spell scientific notation. There it is. SCIENTIFIC. Okay. Okay. I had an English professor that said, you're not a bad speller unless you don't know you spell a word wrong. I liked that definition, because I often spell words wrong, and I think I know I spell them wrong. Okay, scientific notation. So let's try it. Keep clicking the wrong thing. This is a tricky question. So Earth is about 2.57 times 10 to the 7 miles from Venus. Notice that's in scientific notation. And then it's about 4.67 times 10 to the 9th miles from Pluto. So if we were to climb in a rocket ship, we would have to travel that far to get to Venus. And if we were trying to get to Pluto, which is what the furthest planet from us, when the orbits are what they are, right? That's this one. And the author says, well, how many times further away is Pluto? About, right? We're just going to guess. Well, we can just look at, we can ignore this part. And we could just look at this and say, oh, there's a difference of 10 to the second power between these two, right? So we got 10 to the 9th divided by 10 to the 7th, which is 10 squared. And 10 squared is 100 times. So they're about 100 times apart, 100, that many. But then if we look at these numbers, if I multiplied this 2 by 2, I'd get 4. So it's really about 200 times difference. Although we could round this to a 3 and this to a 5. And then it's a worse number, 3/5 times 100. Really, when you're thinking about how many times blank, you want to think about dividing. So if we want to answer this question exactly, what we want to do is say, take this 4.67 times 10 to the 9th and divide it by 2.57 times 10 to the 7th. And this is exactly how many times further away Pluto is than Venus. So I want to show you how to do this in Desmos. So everyone travel yourselves over to Desmos. And let me show you how to type these numbers in there. It turns out that when you're working with a calculator, scientific notation is just, you just type it as you see it. This is an operation. So I'm going to type 4.67. I'm going to hit the times button, and then I'm going to do 10. And for me, I'm going to do Shift 6 and 9. That's how I get an exponent in Desmos. But you can also use this AB button. I'm then going to put this in parentheses and divide. And now I'm going to do the 2.57 times 10. I'll use the AB button that creates that exponent to the 7th. And you can see that we weren't too far off in our estimate. This is approximately 182 times further away. Notice I rounded to the nearest whole number. So because the 7 was larger, I added a 1 to the 181. So they're about 182 times further. How we doing? Does that seem okay for you all? So here's an explanation of how to write things in scientific notation. I'm just going to show you right here. Awesome, Latoya, thank you for that. So for questions 2 and 3, we're just writing this number in scientific notation. So I'll do the first one, you all do the second one. First trickery is you got to find where is the decimal point. And when you're working with numbers like this, I did Shift 6 to get that caret button. It's this one. I have a full keyboard. I think it's Shift 6 for everyone. If you're using your keyboard, otherwise, when you're in Desmos and you open up this keyboard, the keypad, it's this A to the B thing. That's how you get an exponent. So let me write this number down with all its wonderful commas and all that. And then the decimal place, if you don't see one, is at the very end of the number. Awesome, Latoya, awesome. So when we do scientific notation, we want to write a number between 0 and 1. So when I look at this, that means I need to move the decimal to here. In other words, the number I'm going to write is 3.29697. That's the A part in my A times 10 to the n power, right? Come on. A times 10 to the n. This number is between 1 and 10. 3 is less than 10, it's greater than 1. Now, what I have to think about is how much smaller did I make this number? How many times smaller? So it's 329 million and it became 3.29, right? So it got a lot smaller. Well, one of the ways we can do that is just counting. How many decimal places did I move this thing? 1, 2, 3, 4, 5, 6, 7, 8. I moved it 8 times. So if I want to keep this thing to be the exact same number, I need to write it as 3.29697 times 10 to the 8th, because I made it 8 times smaller. Technically, I took this number and divided it by 10 to the 8th power. That's 10 million, and got this amount. Awesome, good. So write number 3 in scientific notation, y'all. When you have it, type it in the chat. Love it. Yep. 2.389 times 10 to the 5th power, because we moved it 1, 2, 3, 4, 5. Awesome. So notice what we've done here. This is how we're going from scientific notation into decimal notation. And decimal notation is the one you're probably most familiar with. It's the one we use the most in life. Okay. Now that's also large numbers written in scientific notation. So numbers much larger than 1. What happens when we go in the other direction? What if we're wanting to write tiny numbers? Well, that's where we get negative exponents. A negative exponent means divide by this number. So when we have 10 to the negative 1, that really means 1 divided by 10. Or 10 to the negative 2 really means 1 divided by 10 squared, or 1 divided by 100. That's 10 times 10, and so on and so forth. So what that does is we can take really small numbers and then write them with a negative exponent. So here we have this one. In some ways, this is easier because the decimal point has to be in the number already. It's visibly there. Whereas in the large numbers, the decimal point is not visibly there. You have to remember, oh, it's at the far right. But we do the same thing. We got to count how many times did we move this decimal. So I've got once, twice, 3 times, 4, 5, 6, 7, 8. So when I look at this number, when I write scientific notation, I have to start with the 8 because that's a number between 1 and 10. And then I just have to figure out, well, how many powers of 10 am I going to divide by? And that's where this counting goes. And that happened to be 8 times, so I put a negative 8 up here. This one, same thing. Notice the only numbers, non-zero numbers we have in here are 12. So I know it's going to be 1.2 times 10 to some power. Notice I wouldn't have put the decimal all the way to the right of the 2 because that would have been a 12, which is larger than 10. And then we just count how many times. So I've got 3 times, this is 3, this is 3, and then 1 more to get to there. So that's times 10 to the negative 7. Notice this is saying a typical flu virus measures between these 2 meters in length. Now we could have written that in centimeters and that would have made it a little less tiny, but even that is quite tiny. So when researchers are looking at the flu virus in your blood, it's really hard to find. You need that incredible magnifying glass. Same thing here. Here we got 7. This should be 7 times 10 to the whatever power. And I'm counting 3 here. And then I'm counting 3 more. Excellent, Jennifer. That's 10 to the 7 times 10 to the negative 6. Now, I want to see if y'all can do this. Based on the size of the exponent in scientific notation, which is bigger? Small flu virus or typical E. coli virus or E. coli sample? What do y'all think? Okay, why E. coli? Or maybe we don't need to answer that. We just need to state that this number is larger than the small. Well, let's use the largest piece. Is larger than this one. And that can be tricky, right? Negative numbers flip the script on things. So the smaller the absolute value, like 6 is smaller than 7, but negative 6 is larger than negative 7. And that can mess with your thinking sometimes. Okay, how are we going to calculate this? Or can you calculate exactly how many times bigger is the flu virus compared to the E. coli? Now it said the small flu virus, so I'm actually wrong here. I should have done the 8 times 10 to the negative 8. That's the smallest one. Calculate that one for me, y'all. Okay, Jennifer, how'd you do it? I think you're right. What we do is we take the bigger number and divide it by the smaller number. And that tells us how many times larger one number is than the other. So let's do that. 7 times 10 raised to the negative 6 power. Did y'all see how I wrote that? Notice Desmos gives us that scientific notation in decimal notation. And you could have typed this in decimal notation too if you wanted to. Sometimes that might actually be less typing than what I'm doing, which to me is the only reason one might do one version over the other. Oh, you crushed it, Jennifer. Good job. So it's 87.5 times bigger. And that's this. This is one of the skills I want you to have, is to be able to take numbers and work with them in Desmos. And I'm going to give you numbers in scientific notation and ask you to do calculations with them. Okay, let's go the other direction. What if I have a number in scientific notation and I want it written in decimal notation? And for this one, what you're doing is just multiplying times 10 to the 6th, which has the effect of moving the decimal place 6 places to the right. So we do this counts as 1. And then we have 5 more zeros to add. 1, 2, 3, 4, 5. So here's our number, 5,400,000. That's the number of red blood cells per microliter of blood in an average healthy man. And then here, because it's a negative exponent, we're going to the left, and we're going to move the decimal place left once here, and then we have 8 more zeros in front of it we need to add. So this one's a little more tricky because we have to start with the decimal. I need to count out 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then 3, 6. So there's that number in decimal notation. Now I want to note something in Desmos. So with this first one, I could have put 5.4 times 10 to the 6th, and it writes out what I wrote here, the 5,400,000. So it gives us the decimal notation. But watch what happens when I write in the other one. Oh, it just gives me this. What? Yes, your calculators are programmed to only give you up to so many decimal points. There's a line that's drawn in the programming where it switches from exponential or from decimal notation to scientific notation. And that line is the 10 to the 9th power or 10 to the negative 9th power. So you're going to have to know how to write things in decimal notation if you're considering relying on your calculator to do it for you. At some point, it won't do it for you at all. Which then leads us to this little thing. If you're using a TI-84 or even some other calculator, you will often see this little E and then a number after it. And what that stands for is scientific notation. So this is how a TI-84 writes scientific notation, which looks like this in decimal notation. So just be aware of that. That might show up somewhere. This Excel will do this. It'll write E to a power as scientific notation. So it's a pretty common, another common way to write scientific notation with technology. Okay. Here is what I wrote out at the beginning of class. 100,000, million, billion, trillion, and then the corresponding power of 10. I would like you to write these out. Write them out in words. So I'll do the second one in 1940. So what this is the size of the national debt in dollars for a set of years. So back in 1930, we were $16 billion in debt as a nation. Compared to where we are now, that's 0%. Like the relative difference is crazy. Then in 1940, notice it's times 10. So this would be $51 billion in debt. Let me do one more. The next one would be $25.7 billion in debt. All right, you all fill in the rest in your little notebooks. Let me give you like 5 minutes, so I actually give you some time to do it. Set a timer for 5 minutes. How are we doing, y'all? Anyone know the answer for 1960? I should also say there's another way we could write these things. So I feel this. So let me see. I wasn't super confident that I was doing that right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's check this one. Yeah. So Jennifer, I screwed up. My answer here is wrong, which if you were following that pattern, you would feel like you were getting it right, but because I did it wrong, I was wrong. Mike is right. It's 286 billion. Oh, that's an awful sound. Because this was times 10 to the 10th. So this should have been, that is my bad. This should have been 257 billion. Which makes this one 286 billion. So what I did to fix my mistake, sorry, because then you probably messed up all the rest, but you didn't, I did, was I actually wrote out the decimal notation with the 11 zeros. So that makes this one 371 billion. And then suddenly it jumps to 908 billion. And then what is this one? So if we use it in terms of billions, this would be $3,233 billion, or 3,233 billion. Same thing here. This would be $5,674 billion in debt. I mean, look at the change. Look at the increase in debt over these 10-year periods from 1980 to 1990. I mean, that's a crazy change. And from 1990 to 2000, again, it's almost doubling. And then from 2000 to 2010, look at that, it's 13,562 billion. Again, that's like a doubling of debt. That's actually more than a doubling from 2000 to 2010. And then from 2010 to 2019, we got $22,618 billion of debt, or 22 trillion. Looks like it got slowed a little bit between 2010 and 2019 in terms of doubling. Didn't quite double, a little bit less. So yeah, there you have it. Crazy change. We're going to do some stuff in chapter 2, unit 2, with the debt. We're going to look at try to model this debt and see if we can't predict how it's going. Okay, here's a graph of that debt. Yikes, right? Look at that insanity. What happened right here? What did we do wrong? Okay, I really like this question. It says the population of the United States was roughly this back in 1930 and roughly this in 2019. So if we were to pay off the debt by just making every US citizen pay a certain amount, how much would each person have to pay? Yeah, it could be war. Yeah, I don't think I'd argue with that. Although war makes lots of money, so it helps the economy, but it also increases spending. Yes. So what we're going to do is we're just going to take these numbers and divide. So notice what we're doing is we're calculating a unit rate. And that unit rate is dollars per one person. That's what we're trying to calculate, which is what we did back in Unit 4. So for 1930, the number of persons, and I don't know where he got this number, is this 1.23 times 10 to the 8 people. Yeah, and then the debt there back in 1930 was this 1.6 times 10 to the 10th. So how much would we have to pay off then? Well, let's figure that out. That's what Desmos is for. 1.6 times 10 to the 10th divided by 1.23 times 10 to the 8th. What? That's it? Does that blow your mind? All we had to do is have every US citizen pay $130.08. And we would have been a debt-free nation per one people. What kind of English is that? Terrible English. Per one person. Man, why didn't we do that? I think there's a couple of things to think about here. I have a 4-year-old who is a US citizen. And I believe when the census happened back in 2020, they are counted in the total population of America. So this $130.08 is per person, that is at least however we counted the census. So my 4-year-old has $0. So I would have to make that payment for her. And my 8-year-old for that matter. Great question, Jennifer. I pulled it from here, the 1930 debt in dollars from this table. That's where I got the 1.6 times 10 to the 10. Okay, and then the other point to make
I got a question.
Yeah, go ahead.
Oh, you got the 1.610. Oh, never mind. Never mind. I'm reading it wrong over here.
No worries. Okay. I have already proven that I get things wrong, so it could have been me. The other thing to think about in terms of this $130 is what would $130 have purchased back in 1930? Definitely a car. I don't know. I don't really know with inflation and all that, the difference between them. Okay, now we're going to do it for 2019. So for 2019, the US population, notice it's almost doubled. No, it's more than doubled. So we went from 1.3 times 10 to the 8 to 3.3 times 10 to the 8. So that's a little over, multiply this by 2 and you get 2.46. So it's a little over doubling. And then here's our debt. Ooh, 2.2618 times 10 to the 13th. 2.2618 times 10 to the 13th. That got crazy bigger compared to 1930. So get ready, get your checkbooks out, because we're going to turn off the debt. That should be a 13th there. I think you can't see it very well. There we go. Divided by 3.3 times 10 to the 8th. Ooh. Yikes. So $68,539.39. And we can pay off our debt, our national debt. Which in some ways, like, doesn't seem like that crazy of a number, but then I couldn't pay that. For most in America, that is far more than they make in a year. If you look at the median income, that's an unattainable number for most Americans. And I'm talking households. So this 68,000 would be for me. It would be for my 4-year-old and my 8-year-old. Like, it's just It's crazy. And I should be writing the units on this, shouldn't I? And this should be person. Person. Okay. So what I have done in the worksheet to have you practice this, which is what I want you to do now. Unless, are there any questions on this? Do y'all feel okay? You see how to type it in Desmos? You're feeling good about all that, right? Let's go to the worksheet now. And let me give you like 10 minutes to try it. Maybe 10 minutes is too much time, but we'll see. Let's do 5 minutes. So here, this should really say change instead of difference. They mean the same thing, but we've been using the language change. And Maya, this goes to your question at the beginning, so I'm not going to say anything because I want you all to taste it and see if you're understanding the language. So I've given you two numbers, by the way. If you want to click this link and see, this is the debt clock. If you want to see where we are now in terms of debt, we're at $30 trillion in debt and counting. And the government brings in $4 trillion a year, which is roughly 14,000 per US citizen, if we averaged it out. This can be kind of a terrifying thing to look at. Essentially what happens is if all the people who hold US debt call it in, the world collapses and money no longer matters, right? It's food and bullets is probably what matters. But we don't need to worry about that yet. So try out this worksheet. Let me get out of the way. This is on page 16. So let me give you 10 minutes and I'll hang out and answer questions. So we're 5 minutes in. Does anyone have, how y'all doing? Need more time? Should I keep quiet for the full 10 minutes? Well, let's do it. First, tell me, what did you all do to calculate the actual change?
So I just left out the 10 to the 13th and just did the difference between 2.83545 and 1.96279 and then added the zeros after.
Love it. Whoops, I forgot a decimal place. Love it. So you had 0.87266 and then added the 13 zeros. That's
Yes.
perfectly acceptable answer. So let me see if I can. So first, yes, stepping back, you correctly applied the formula, just new minus old. How much debt was there an increase between 2016 and 2021? So it's the answer in scientific notation is 8.7266 times 10 to the 12th. And you could have done this, Mike, your option was perfectly acceptable and well done. You also could have just typed them in scientific notation as they were and gotten the same thing. And then, right, you have to write the final number in decimal notation. I should have made you write the words for it, but whatever. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. What is that? $8 trillion increase in debt from 2016 to 2021. June 6th to June, or June 1st to June 1st. So that's the actual amount of increase, which, you know, depending upon who you are and what you're trying to say, this might be an effective means of trying to say things. So Jennifer, your thing, I like what you said. Oh, you took the 2021 number and divided it by the 2016 number. What were you calculating with that? That's a legitimate number. Well, yeah, you didn't answer the question here, but that number is how many times bigger is the 2021 value relative than the 2016 value. So it's a 1.444601 times bigger, right? It's just a 1.4 increase. What we want for relative change, does anyone know? Well, does anyone know what we want for relative change? So this answer isn't the correct answer for relative change. It's the number of times larger the 2021 value is than the 2016 value. What we want for relative change, which is a different number, and you're going to see how they're related, by the way, that's that new minus old divided by old, and then times 100 to turn it into a percent. So here is the new minus old number. We just have to divide that number, this number right here, by that original number. So I'm going to put in parentheses this, and I'm going to divide it by the 2016 number. Now look at this number and compare it to the number you got. Do you see the similarities? Can you explain the similarities between the two? And then of course we multiply that by 100 to get the percent change. By the way, this is not very clear language, right? Between the 2 years, it should really say between 2016 and 2021, which is a 5-year change, right? This is, let's say 44.46%. So do you all notice the connection between these two? Does anyone want to comment on that? Like, watch this. Oops. If I subtract 1 from this one, I get the exact same number. What's up with that? And if you have no clue, if you're like, I have no idea how to answer that, Eric, you tell me that too.
What are we answering now?
Great question. That's an even better question. We did the new minus old divided by old, the relative change formula here, and got 0.444, blah, blah, blah. And then Jennifer had done the 2016 number divided into the 2021 number, this right here. So the 2021 divided by 2016. And there's a connection between these two numbers. And I'm wondering if anyone can explain, if anyone understands the connection between the two. Totally fine if you don't.
I think the second number is the percent change that, like, because it's 144% times larger. So I'm not exactly sure what the term is for that.
Love it, Mike. Yeah. So that's the crazy thing. They are the same. Like, we could literally take the 2016 number and multiply this, and we get the 2021 number. So what this number is, what this first number is, it's the percent increase. There's a 44% increase in debt from 2016 to 2021. Or we could say 2021's debt is 144.46% of 2016's debt. Now, we could use that to try to mislead people, because the division one sounds way worse than the relative change one, right? What we can't say is there was a 144% increase in debt, because that's not true. It's 144% of, which represents a 44% increase. Do y'all see that subtlety there? Someone could lie and say there was a 144% increase from 2016 to 2021. And while the number, the percentage is correct, the interpretation of it is wrong. It's not a 144% increase, which leads to what you're supposed to do here. You're supposed to explain the change in the context of the situation using words to state the number. That's this number. And you can just say there was an $8 billion increase in debt. And then here you're supposed to explain the relative change in the context of the number. That's the when, what, and how much. And there you're saying that the US national debt has increased 44% from June 2016 to June 2021. How are we doing? Y'all doing okay, or is this just getting crazy? Like, Jennifer, do you feel better after that explanation? Okay, Maya, what part? I know this is quite confusing. Maybe if I wrote things.
I don't understand how to explain where I'm lost. I just feel lost.
Okay.
Like, I guess when you go back to finding the relative difference between the 2 years, all of that, and afterwards, I'm just in space.
How about I label stuff here? Relative change. And let me just write out an explanation. So the US, the total debt increased by 44% from 2016 to 2021. How do we feel about that statement from this relative change formula?
That makes sense.
Okay. So then I think the crazy part is like, what's up with this? So here we could say, oh, that's not what we want to do. We want to do a note here. Here we want to say, let's see, 2021's debt. Oh, let's do it this way. The total debt in 2021 is 1.44 times more than the debt in 2016, or 1.4 times larger. That's a better word than the debt in 2016. How does that feel?
I understand looking at it, and I mean, the statement makes sense, but I still don't understand why you divided the new debt by the old debt.
Well, so yes, I didn't, but I wanted to point out that if you do that, which Jennifer, you did that, and it's a legitimate number. This is the answer to C, by the way. The total US debt. So this is C's answer. Let me just label that. If you were to do that, you're getting a useful number, and it is connected to the relative change formula. You're getting the number to multiply by to get the new one. So if we took, you took the new number and multiplied it by 1.4, you would get, or sorry, if you take the old number, in this case, the old debt, 2016, oh, come on, 2016 debt, and you were to multiply it times 1.4, you would get the 2021 debt. And it's about the semantics of things. Buried within this multiplier number is the percent increase. It's just including 100% of the original amount. That's what the 1 stands for. It's take the original amount and add to it this percent increase. Which is a tricky thing, right? And this is where I'm trying to push you all to go beyond just a memorized formula, but to see what is it that these formulas are doing? What is it that they're calculating? What is it the information you're getting? And I totally get that that gets crazy. Did that help at all, or did I make it worse? It helps a little. Okay, a little. Okay. All right. How do you all feel about your answers for the 1-6 worksheet? Are we feeling happy? And I should say, I want you to know how the formulas work and be able to use them and how to interpret the results. So what we're talking about here kind of goes a little deeper than really what this worksheet is asking you to do, which is just new minus old divided by old. Tell me what those numbers mean.
I think I'm getting C and D mixed up as far as which one is looking for what answer.
Oh, well, Mike, that's not your fault. That's my fault, because I just told you the answer to C is here. I'm like, here's the answer to C. No, this is the answer for D. D is the relative change. C is the actual change, which is this number. So the answer for C should just be, it's an $8 million increase in federal debt. Debt increased by, did I say million? Trillion. $8 trillion. Thank you, Mike, for making that clarification for all of us. So essentially what this is saying is, people in charge of the government during this period of time added $8 trillion to our total debt. And then we could do this same calculation. And this, of course, doesn't this straddle a couple of administrations? This is the Trump administration and part of the Biden administration, right? I can't remember. Actually, no, I think this is all the Trump administration. And then you can do this kind of calculation for each administration, and you can look at how much debt did they add based on their spending policies. And yeah, there's more that has to go into that thinking, because there's some spending by the US government that is not actually determined by the current administration. It was written into law by all previous ones. So there's lots of politics that goes into money, right? That people try to shape narratives particular ways that often are quite untrue. Okay, have I helped you all clarify things, or did I just make it worse? Did I make you all so lost that you don't even know what question you want to ask, or do you feel good and you're ready to move on?
So if I'm understanding right, on C, we need to write out 8 trillion, like the exact number, or just put 8 trillion?
You could just do 8 trillion. Did I round it appropriately? It should really be, so if you're going to do, I'm incorrect. I should say 9 trillion, about 9 trillion. And if I want to be more accurate, I could say 8.7 trillion. That's really going to be the better number. You could write every single word if you wanted to. 8 trillion, 726 billion, $600 million.
Okay. That makes sense.
Nice, Mike. Yeah, thank you for that. Go ahead, Jennifer.
I have a question. For like, if it's, because the wording I think screw me all up. So if it's like, if it asks for the actual difference, then you minus new to old. And if it's asking for relative distance or difference, you divide.
You do new minus old divided by old. Yeah. This formula. So I get to what's getting you here, because at the beginning we did the division, right?
Yeah.
And that's a different question. That says, if I ask you how many times bigger is something, you're dividing the big number by the small number, and that's the number of times larger. or the number we multiply by. Whereas relative is using a percent version. And that's what I was trying to help with back here, is this idea of what happens when you divide two numbers. You're getting what number you multiply by between them to get the other one, which is a different thing than when you're calculating the change divided by the original, new minus old divided by old. And it doesn't help that they're all connected, right? Other questions? While you're thinking of questions, let's make sure we check in on the lesson check for 1-6. I've had folks emailing me about it. So let's make sure it's the right one. And we can all get it right. Mhm. Mhm. There we go. Oh, come on. I don't think you all have to do this push notification, which is nice for you all. Okay, so we should check to see that it's even got the right due date on it. We're looking at, yeah, the 25th. So 1.6 lesson check. Unlimited, highest, wonderful. We're going to do the preview. Says answer question 7 on page 94, the number of red blood cells. So that's this one that we did back here. Was it down here? No. Right here. So this is the 1.6 lesson check. And you're just typing in this answer, 5,400,000 red blood cells. Submit quiz. Yay, I got it right. Looks like I didn't even have to put in let's see, it looks like I didn't have to put in the commas. Oh, it did it automatically. Well, that's fun. I wonder what happens if I do put commas in. I think in
put
Jet.
commas in and it still gave me it correct.
Nice. Well, that's very nice. I remember JetNet would count things wrong, I think, if there were commas. I don't know. Awesome. Okay. So we've completed unit 1. So what I would like to do in the last 45 minutes of class is to write up a review of unit 1. And then one of your practice assignments that's going to be graded for as you prep for the midterm, which is not until after unit 2, so it's a long ways from now, is the unit 1 review B. So if I get to the right page here.
I believe it's page 58.
Thank you. Where's the jump to button? Page 58. Here we go, pages. Yep, here it is. This is a graded assignment that you will submit. We're gonna probably take some time to do. We might take some time to do Unit 1 Review A together, and if we don't, it's done. There's a YouTube video where I work it out for practice problems, and this is how you prep for a math exam, as you work through problems, but then you need to be able to know if you got it right or not. Okay, so there's this assignment. I believe this is set to be due. Let's see, what does it say in here? I think it's not this week, but next week. I'm probably going to make it the same due date as, here it is, Unit Review B. It's currently set to be the 25th. That might be a little ambitious, but maybe let's leave it for now. And we can see how you all are doing. And then you've got your project that you're working on that's also set to be due the 25th, but maybe we should push that forward a little bit too. So let's first write up our review of come on. Our review of Unit 1. So let me also clarify what I'm doing here is I am suggesting what you should have on your reference sheets when you take the midterm exam. Remember, you're allowed 3 pages of anything you want to write up when you take the midterm. And there is no limit what could be on those pages. Those pages are double-sided, handwritten, and then I'm writing the kinds of things that you need to know. So often students try to cram everything they can, or they ask, can't we just put the whole textbook in there and whatever? And that isn't quite as helpful from what I've seen. Mostly what you want to do is write general rules and maybe have an example of what's going on in those problems. So any questions on that? Do y'all feel good about what's about to happen here? Okay, so I'm going to go lesson by lesson. So in 1-1, one of the first things you need to do is be able to go seamlessly between a percent and a decimal. So you need to know how to do that kind of thing. I'll hand you percents and ask you to do calculations with it. So that requires you to convert that percent to a decimal. Recall that it means to divide by 100 or multiply by 100, depending upon which direction you're going. And then there were a variety of percent problems that you encountered. So one of them was just percent of questions. And that's where you take the percent, convert it to a decimal, and multiply. And the other was find the original amount. And that's where maybe I give you a percent discount and you use that to find the original. Or maybe I give you the sale price and you find the original. So there's a bunch of variations of this. Find an unknown given a bunch of others. Great question was asked. Are we required to turn in Unit Review A? You are not. I think we will have time in class to work through that together, and then your job would be to do Unit Review B on your own. I always am happy to answer questions on those reviews. So please bring those questions to class or to tutoring hours, etc. And then the other question that came up in here was the percent change formula. That's new minus old divided by old. And then with that was the interpret in context. So what I've written here is useless, right? Like this is not what should be on your reference sheet. Your reference sheet should be the rules for how to do these things. And if you feel like you need example problems on there, that would be great. All of that. Any questions on that? Does that seem familiar to you all? 1-2 is essentially what your project is. And that's, so there's not going to be any create a graph, a pie graph, or create a bar graph like there is in 1-2. So really the kinds of things from 1-2 is reading bar and pie graphs, and then doing percent and degree calculations from bar and pie graphs. So maybe I give you the total number of items in the bar graph and ask you how many are in a particular sector. Or I say how many degrees would make up this sector, that kind of thing. So it's these problems here are essentially this same problem that you're doing back in 1-1, calculate a percent of. 1-3 is even less, because 1-3 was like, how do you estimate things? And this is related to reading bar and pie graphs. So I'm just going to give you kind of a bad pie graph and ask you to guess some numbers off of it based on your understanding of a pie graph. It's like the 1-3 worksheet where you're estimating the number of cannabis locations, brick and mortar dispensaries, cannabis dispensaries in a particular state. 1-4 was what everyone hated, right? 1-4, there's a couple different things you need to know. You need to know, what do we mean by an equivalency statement? And how does that equivalency statement inform what you do with conversion factors? And what are conversion factors and how are they used? And of course, those two words go with the concept of dimensional analysis, which is using the units of numbers or the units of things to convert between various measurements. Yeah, Jennifer, that's not a bad idea at all. What I'm thinking, what's in my head is, as you work through the Unit 1 Review B, being able to identify the similar questions in the homework and compare the work you did there with the work you're about to do would be super helpful. Which also means I need to get all of that work graded like yesterday so that you can have some feedback on whether or not you got it correct. For those of you here who regularly attend class, I'm not particularly worried because we just did the entire worksheet, right? So you all know the correct answers. It's more the people that aren't able to attend and maybe aren't able to watch all the videos, that kind of thing. I don't know if that's helpful.
Can I ask, what is our exam going to look like in terms of how we do it?
Great question. And I don't know if I have the full answer yet. I think what I did in the past is I wrote, it was like a lesson check. All the questions were lesson check questions, and you typed your answers into the computer, which isn't great because the grading, it's very different than how you do it on a piece of paper, right? But it was the best option for this kind of digital world, in my opinion. So It may be that again, where there's a lockdown browser that only allows you to work with Desmos and the particular thing, so you're not allowed to surf the web for all the answers. Not that that's super helpful for these kinds of exams, but sometimes it is. And then there's ones where I have to grade, like where you type in a sentence and things. So that's what's been done in the past. I know my colleagues in the stats world, we do a Zoom meeting where everyone logs in on Zoom at the same time and takes the exam, and I just sit there and watch, and it's like a pencil and paper exam. So I don't know. I don't like that option because we all have to be on at the same time. And this is a class of 60 students roughly. And with 6 out of 60 or 5 out of 60, that it's very unlikely that we're going to find a time where we can all meet. So I think that's what's going to happen.
Do you think we'll have like a time limit set on it, or?
So I do put time
Okay.
limits on it, but it's usually like a long time limit, like way more than people would need. So I write the exam for the typical student to take, an hour and a half, 2 hours, maybe. Not like, it won't be any longer than the Unit 1 review. In fact, so to your question, Jennifer, that Unit 1 review used to be an actual unit exam. That's what I handed out in class back before COVID happened. And so that has how many questions are on that review? I think it's like 10 or 15 questions spread over 10 pages, where it's double-sided and all that mess. Yeah, this is 10 questions. So the midterm might be close to that, maybe a little bit longer, probably not too much longer. In fact, last time the midterm was super short and most students took under an hour to take it. But you want to plan between, well, if you think about pre-COVID, it was a class period that you took the exam. And so I would try to write it for the middle student, the middle speed test taker student, to take roughly 2 hours, probably a little less. But then I give a time limit, say, of 5 hours. What I want to happen is you sit down and take the exam and finish it, and then walk away. So I'm not allowing the exam to be started and then stopped and then come back to. I think that can get students in trouble. You want to go talk to other people about it, whatever. But I'm not interested in time being a factor in your exam score, if that makes sense. So I don't think anyone is going to run out of time to take the exam. It has never happened. Because if I give you 5 hours, right, that should be more than enough. That's my thought. The other thing in 1.4 is the idea of a rate versus a unit rate. Remember, a unit rate, the key thing is at the bottom is just 1 unit of whatever we're talking about, and then the top is whatever units. And then we often did dimensional analysis with the unit rates or the rates to convert between things. Think about that kind of crazy 1.4 worksheet. Did you get your question? Did you all feel like you got your questions answered for the exam? Remember, it's the midterm, so it won't come until after Unit 2. I'm just writing up what will be on that midterm from Unit 1. And we will, of course, when we're done with Unit 2, we'll review Unit 2 and talk again about the midterm as a whole. 1.5, we didn't add anything new, really. We talked about, here's where we talked about change, which I guess was new, and then relative change. And we also added in here error and percent error. And remember, for this one, it was the estimate minus the actual divided by the actual. And then finally, today in 1.6, we added in the concepts of scientific notation. And you need to know the words scientific notation. How does that interact with, how does that relate to decimal notation, and how do you go in between the two? Oh my goodness, I do not know what's going on with my spelling today. And then calculations with them, how to calculate and write them out. So what you have here, if you look at this Unit 1 review, these questions are the types of questions that you're going to face on the midterm. And if you look closely at them, you'll find that they're essentially the same questions you were doing in the worksheets. And that's one of the nice things about these having the same author. Myself and one of my colleagues that I work with wrote the worksheets, the reviews, and we write the exam. So those all line up quite nicely. Whereas Alex is not written by me. And so those questions can be framed, or probably phrased a little different, and might look a little different. But same concepts, same questions. Okay, so what kinds of questions do you have for me about all this, for starters? Let's start there. Did I make it so you all, did I write this too fast? Did everyone get a chance to write it down or whatever? How would I even save this? Maybe I can post that for people. How are your projects going? I'm going to do something real quick while you think about that. Has anyone started their project? Have we talked about the project yet?
Would you mind briefly going over the project again? Because I don't think I've started it yet.
No worries if you haven't started it. I just want to make sure I have talked a bit about it. My in-person class said they wanted to see an example of the project. And I hate doing that because then everyone thinks they have to make their project look like that particular project, which is not true at all. But it's also sometimes nice just to see what someone else did as a means of comparison. So let me grab an old project that got 100%, and we can glance at that for a second. But I'll pull up the full project too, and we can talk it through. Okay. Awesome, y'all. It is definitely worth talking about again. Let me share my screen before I start doing this so you can all see where to get things. So just as a reminder, the write-up for the project is here under projects. This is how you download things, where it says download, and that's really the only way to edit in Word. I don't think Canvas allows you to edit much in there. I could be wrong. I don't quite know. So remember, the goal here, or the first thing you're doing, is you're planning your life. You're going to plan your time. And that involves writing up a schedule that involves determining, like, categorizing your life. How do you spend your life? And you're thinking of kind of large bucket items. You can get as crazy as you want, but if you're like, I spend this much time brushing my teeth, that's probably less than an hour of your time. I don't know, maybe not. And so you're creating a daily schedule for 1 week of how you use your time. And then in some sort of electronic method, I think is the best way, you're going to create a 24-hour schedule of your week using your categories that you created. And then from that, you're going to create a table with your checking your hour usage for each of those categories. And then each of your subcategories. And you need the percent of each day that's being used and the number of degrees for each category. And then you're going to create pie graphs of that. So here's an example project that someone turned in. It's quite amazing, if you ask me. Don't feel like this is how yours has to look. So they have their 24-hour period here, and they've got their 7 days of the week here. And here are the categories they created. Here's the total time they spent. It really should be weekly time. This says day, doesn't it? Calculate in percent of each day. This should say week. Really, I guess it could be day too. I don't know. I think it should be week. This person did it by week. And so here's their total time. It adds up to 168 hours. Here's the decimal version of the percent of the week. Here's the actual percent of the week. And here's the number of degrees that make up this pie graph. And here's their pie graph that they made. And here's their bar graph that they made. Now they did a planned time, and then they tracked themselves for how they actually use their time. I did not ask you to do this. You didn't have to create a thing of how you actually use your time. Your job is to just pick one of the categories and keep a time journal of your usage for 1 week. And then you're creating so you're just tracking one. And then you're going to do some analysis. You're going to create a bar graph of your main categories for your planned and your category for actual time. And then you're going to pick and compare that and calculate some actual difference. I keep having this difference language in here. It should be change. That's the language we've used. And you're going to interpret that number in context, just like we did in the 1.5 worksheet. And really, this should be error because you're guessing, you estimating your time, and then you're tracking your actual time. And then you're going to do some analysis of like having done all this mathematics of organizing and looking at your time, what did you learn essentially? So take some time on this, put some good thoughts on this. This is a large portion of the grade. And then the last task is a dimensional analysis task where we've given you all the information and you're doing some calculation. I had one student say, what am I doing for question 5? Really, it should look like this. The question in number 5 is using the weight from question 1, how many pills should you take? And this information. And the work here that you can show, I think I showed this to you all, is copying and pasting what you've typed into Desmos. That can be your work, or you can write it all by hand. Questions on that? That was kind of a really brief, fast overview again. I don't know if that's super helpful. Hopefully this was kind of helpful. The project has changed a little. We don't do task 4 anymore, and we didn't have the other task in here. Here's how they showed their work. And this was their analysis. This was a very, very busy individual. My screen just froze. What's going on? And some of my in-class students, I had one student show me how they were organizing their project, and it was very, very different than that schedule, which is totally fine. That schedule is essentially a copy of what's in the textbook. and you do not have to do that. You have full creativity. So what questions do you all have?
I know how you feel about due dates, but just so I can have like something written in my planner that is due on, you said the 25th?
Right now it's set for the 25th, but for my in-person class, I changed it to 2 weeks of time on that. So I made it the 2nd. I don't know if that feels better for everyone. We're still going to keep moving forward with unit 2, but it might be nice. I don't know. Maybe I should just leave it the 25th to add that pressure for everyone. Now, what do you all feel?
I think a little bit more time would help me out because I don't have to, because I have to do the Alex stuff still.
So we have differing opinions. Leave it the 25th or move it to the 2nd. Oh, 2 votes for the 2nd. Here's the question. If I move it to the 2nd, are you going to start it on the 1st? Or if I leave it on the 25th, are you going to start it on the 24th? For me, I don't care about the due dates at all, other than I want to keep you all being successful and on track. I think, Jennifer, since there's at least 2 people that said they want it to move to the 2nd, I'm going to go ahead and do that because I've already done it for other classes too. But I can leave it. I think I can do individual due dates, and I could leave yours on the 25th if that would. Like, the reason I say that is I get it. I'm the type of student that needs some pressure. I think if I was a student in my class, I wouldn't do very well, knowing that the due dates are all kind of wishy-washy. I don't know. I always question. I mean, I question everything I do, making sure it's the best. And I have no idea where to land on this. Okay, so I ended up moving it to the 2nd. Yes, Jennifer, you definitely can. You all can turn anything in early, so feel free to do that. Okay, so it's currently due the 2nd, and that I won't change that anymore. And I'll say the other thing I'll say is that the students that get zeros on the projects are the ones that wait till after the due date because they never do it. So that's where I always feel a little guilty that, oh, did my policy of soft deadlines work against students like that? And I think by and large, I'm doing the most good by having soft deadlines. I think more students appreciate it than don't. But I want everyone to be successful. Unfortunately, I don't have a whole lot of power of how to help everyone be successful. It's more on you all. If you can, the more you squeak, the more you come for help, the more I can help you be successful. So take advantage of that. I'm done for today. So if there's anything else that you all need for questions and things, ask away. Otherwise, if you are happy with how things are going, take off. And we'll see you on Wednesday. Don't forget, I have the office hours, 8:30 to 11, Monday through Thursday, virtually, Tuesday and Thursdays, both virtual and in person. Let me know what I can do to help you all. That's what I'm here for. All right. Go ahead, Jennifer, what you got?
When I'm working through Alex, because it seems like I have so much to do, I get a notification that I only have 15 days to do it. And that's not going to work for me. Like, there's no
15 days
way.
for what?
Oh, I'm sorry. I got 14 days left is what it tells me. Modules unlocked, 14 days left. And I still have 73 things. I'm not going to get through that in 14 days. I don't care how good I am. Like,
well, I think there's got to be something wrong. So there are due dates in there.
mm-hmm.
And those due dates correspond to each unit. So either I've done something wrong and I need to fix it, or it's just saying you have 14 days left till the next due date on a particular module, you have till the end of the semester to complete all 24 modules.
Okay, because I'm mainly, because some of these modules are straight making me angry. So I'm skipping through, and the ones I'm doing good, I'm just completing the whole thing.
That's
And
totally fine.
So
Yes.
I'm guessing it's ones that are like, because I'm looking right here, it says Unit 1, Lesson 4 is due October 10th. I haven't done that yet. I was working on completing the ones that I got like a lot of completed already to begin with.
Right, so so good. Thank you for clarifying that. That's what that's doing is I tried to put deadlines in there to keep students moving, because having 165 things to complete by December something is often, people just forget about it.
Yeah.
You don't have to worry about those deadlines. The way you're working through it is totally fine, as long as by the end of the semester you have all 165.
Okay.
When those 14 days pass, if you haven't done those, it doesn't lock you out of them. It just, you can't even see a grade in there because I have it set that you can't. It would give you a 0 for that module because you didn't have it by the due date, but that's not even visible to anyone.
Okay.
So yes, don't freak out about it. Just you keep working on the things you want to work at. I mean, eventually you have to do those nasty ones, and I'd be happy to help you. We could even do them together, like during class time or whatever, look at a couple of them.
Okay.
But you're doing just fine.
All right. Thank you.
You are welcome. Anyone else have questions? Go ahead, Maya.
Hi, Eric.